All right, people. So now that we've tackled systems of linear equations, the last section of this chapter is about systems of nonlinear equations. So we're still, the systems part is still the same idea. We're just going to have more than one equation at once, and we're looking for a pair of values x and y that solve both equations at the same time. It's just that now we're not forcing the equations to be linear. Some of them might be nonlinear. So again, the sort of two guiding sort of methods to solve these are substitution and addition. So let's take a look at this first one. They ask us to use substitution. So they give us this first equation, which is not linear, right? Because we have x squared and y squared involved. So we have x squared plus y squared equals 25. And the second equation, which is linear, is x plus y equals 7. And so to use substitution, well, I'll solve the second equation for either one of the variables there. I picked y in this case. So we said y equal to 7 minus x. And now substitute that back into the first equation. That becomes x squared plus the quantity 7 minus x squared equals to 25. And if we multiply everything out, we get what? X squared plus 49 minus 14x plus x squared equals to 25. And let's see, if I gather up my like terms on the left side, I have 2x squareds minus 14x. And then if I subtract 25 from both sides, I get plus 24 on the left. And so I can say that guy equals to 0. Okay, now I know that each of these three coefficients are all divisible by 2, so I'll divide the whole equation by 2, and I'm left with x squared minus 7x plus 12 equals to 0. And now I believe this guy factors. Two numbers whose product is 12, but whose sum is minus 7 are minus 3 and minus 4. So we get that x equals to 3, or x could equal to 4. So notice the difference here is that now we have two possible things for x. This comes from the sort of non-linearity of this first equation up here. So when x is 3, the corresponding y value is going to be 7 minus 3, which is 4. And when x is 4, the corresponding y value is going to be 7 minus 4, which is 3. Notice the kind of symmetry between the answers. So there's two solution pairs here, 3, 4, and 4, 3. All right, one more using that same method of substitution. They give us here x minus 5y equals to 10. Again, notice that's a linear equation. But the second one, y equals to the square root of x minus 4, is not linear, right? We have the square root in there. No good. Okay. So I think you can use substitution in either way. I believe you could substitute y equals to the square root of x minus 4 into the first equation and solve that way. But I'm going to do the other way. So I'm going to first solve the first equation for x. So we get x equals to 5y plus 10. And I'm going to substitute that into the second equation. So then the second equation becomes y equals to the square root of 5y plus 10 minus 4, which is the square root of 5y plus 6. Okay. And so now we know how to solve equations like this. We square both sides, right? And we have to watch out when we square both sides. We might introduce some extraneous solutions. So we'll watch out for that at the end. So when we square both sides, we get y squared equals to 5y plus 6, which becomes y squared minus 5y minus 6 equals to 0. That guy factors very nicely. We have two numbers whose product is minus 6, but whose sum is minus 5. That would be minus 6 and plus 1. So we solve for y here, and we get either y equals to 6 or y equals to minus 1. Okay, and notice that when y equals to 6, x is going to be 5 times 6 plus 10, which is 40. And when y equals to minus 1, we're going to get x equals to 5 times minus 1 plus 10, which is 5. Okay, so it looks like we have our two solution pairs here, 40, 6, and 5, minus 1. But since we had to do that squaring of both sides, let's make sure that neither of these are like extraneous solutions, right? So, so let's just check them by plugging these values for x and y into the original equations that they handed us. So the first one, when we plug in x equals 40 and y equals 6, we get 40 minus 5 times 6 is in fact 10, and 6 does equal to the square root of 40 minus 4. Okay, on the other hand, when we plug in 5 for x and minus 1 for y, the first equation above becomes 5 minus 5, which is in fact 10. But then the second equation becomes minus 1 equals to the square root of 5 minus 4. Well, the square root of 5 minus 4 is the square root of 1, and that's 1. And 1 does not equal minus 1. So this second solution pair was extraneous. It was brought to us by the fact that we squared both sides and made a quadratic to solve at the end, when really the original equations that we had did not have that, really only had just this one solution pair here. So the only solution pair is 40, 6. All right, excellent. So stick around for the next video. We'll do some addition method of solving these, and then we'll do an application problem as well. So we'll see you then.